Right. I'm going to do just a couple quick problems as a follow-up to the video I just provided, um, which was the physics of motion along a circular vertical plane, like the bucket swinging around, and they talk about the water not spilling out, and some other examples as well. There's a couple that you definitely need to see. In the last video I recorded, I at least showed some of the details about how you can solve for the minimum speed in the, let's say, the classic loop-de-loop problem. Loop-de-loop, like my son actually has a Hot Wheels, whole bunch of Hot Wheels tracks, and he sends it down the track, and then he's got the loop-de-loop. He already kind of knows it has to be moving fast enough as it goes around that loop-de-loop so that the car doesn't fall off the track at the top. He knows if it has enough speed, it'll zip right around that top portion of the circular track and continue around and not fall off. And that ends up being one of the parts that turns up in AP exam questions relating to circular motion specifically. Specifically relating to the top of the path. So I want to just I already went over in the other class, the other video. Again, at the very top, maybe it's the loop-de-loop problem again. So this car is flying along, and we're being asked the question, what is the minimum speed? What does Vmin need to be so that the car doesn't fall off the track? So I'm going to tell you that this thing kind of comes in, of course. It does actually lose speed, right? From an energy standpoint, as you climb a hill, you're definitely going to lose speed. So you're coming in with a much greater speed down here than what you have up here. You're losing speed. As long as your height is increasing, you're always losing speed. But right as you pass through this point, again, you have to have some minimum amount of speed so that you don't have to worry about the car just falling off and crashing down. It will literally continue around the loop. Sorry, I always want to just make sure. Yeah, I'm presenting and recording because sometimes I forget one and then I have to re-record the whole thing. So, all right, I'm good with the presenting my screen and recording. So let me go back. So you should know that when the car is going at just the minimum speed where it's just any slower than this speed, it's going to fall off and crash down here. But at the minimum speed, it just barely makes it over the top and then continues around. At that minimum speed, the wheels literally come off of the track. The wheels literally separate. If we could zoom in on that again, the car's wheels literally come off the track just for a brief moment, and then they make contact again just a brief moment later and remain in contact with the track for the rest of that. But they will separate, essentially fall off the track, but just for a fraction of a second in such a small amount of time that they actually reconnect with the track and then continue back around. And you'd say, hey, that was successful. That's at the minimum, at minimum velocity, the wheels lose contact. I'm telling you that. So let's try drawing a free body diagram. The downward force of gravity is down. Which way would the normal force be? If the car was on the side over here, the normal force would be that way, right? On the bottom of the track, the normal force is up. It's always perpendicular to whatever's underneath you. Well, whatever's underneath you is a track that's this way, then the normal force is that way. In this case, the normal force, if it's going faster than this minimum speed, the normal force is downward. Maybe the minimum speed turns out to be 15 meters per second. Well, what if it goes around this and has a speed of 30 meters per second at the top? Well, it's not going to be separated. It's going to be in contact, and the normal force, it'll be pressing against the track up. The track will therefore push down on the car down, and we would draw the normal force down. And say we've got two downward forces, But at the very special problem that AP wants you to know, the minimum speed necessary. Any slower, it will crash, but it's the minimum speed. In that case, again, there's no contact, no normal force. This is it. This is the only force. And remember that the laws for circular motion says that the net force, remembering that if there is more than one force along this axis here, that inward forces are considered plus and outward forces are considered minus. In this case, we don't have two to worry about. We just got one, and it's technically it's down, right? The gravity force is down, mg is down, and it's plus. It's towards the center. So the uniform circular motion requirements is really, yeah, we sometimes write it like this, but this represents the net force. The net force is called again, it depends on how many forces there are, so it can be confusing. Just know that if there is more than one force, then the extra force in a certain direction, the net force, has to be pointed towards the center of the circle and in an amount equal to the mass of whatever is going around, the speed at that point, which we're talking about now, and r would be, again, the radius of this loop-to-loop, right? So F net equals mv squared over r. The only force, again, that we've identified is gravity. And we can leave it as a positive sign since it's down towards the center of the circle. It's plus. That means we can just re-express that as mg. Not surprisingly, the masses cancel away. In nearly all things, not all, but in nearly all things they do. And again, soon as you suggest that this is moving at the minimum speed and that these lose contact, then I should really have written min. So they write v min to represent that minimum speed. That means we can solve for it algebraically by just cross multiplying g and r. V squared is equal to g times r. Oops, I don't know why I did that. Sorry. V squared, v min squared is equal to g times r, or r times g. And so we end up with, after square rooting, we have v min is equal to, I'm writing it that way just because most textbooks for some reason write rg. It's like you never see f equals a times m, you always see m times a. Well, it doesn't really matter, of course, but I might as well stay consistent with the way you see it written. Usually you see it written in a textbook r times g. But notice it's square rooted. So the 1/2 is square root. So that means the minimum speed is related to how small this circle is. If it's a smaller circle, just a tiny little circle like this, compared to if it's a larger circle, these are proportional to each other. There's nothing in the denominator, right? So it tells us that smaller circles, g is always the same no matter what. What is the relationship? The min is proportional to the square root of r. So that means smaller circular loops require less speed at the top to successfully get through it without falling. Larger circular loops require a greater speed. If r is greater, the minimum speed at the top will be greater. Just generally, that's the relationship between those. But this formula is totally a golden nugget that's worth having in your pocket. It's useful. They're not going to give that to you on the AP equation sheet, of course, by no means. Worth having. So how would we actually solve a problem like that? Well, let's just see. They say, like, here's your loop-to-loop, and the radius is 2 meters, and they'd say it's actually just a little toy thing, and it's a little experiment kids are doing in the classroom. They built this loop-to-loop track with a radius of 2 meters. What speed does the car have to be moving at the top? What minimum speed? What does the minimum speed at the top have to be so it doesn't fall off the track? Square root of r times g. If r is given as 2, and I know g is, let's just call it 10, why not? Then it's the square root of 20, which I know is square root of 5 times the square root of 4, which would be 2 root 5. Right? Root 5 would be 2 in a decimal times 2, something in the 4s. Let's see. 2 root 5, 4.47 meters per second. So that's that's literally how, that's all you, if you know this formula, that's how quick you can calculate the minimum speed to get around the top. 4.47, in that case. Again, if they said, but in the next experiment, it's going to be a wider loop, how will the speed of this car have to change at the top to accommodate this much wider loop? Well, what if R was now, I don't know, 10? Giant one. The radius is 10 meters. 10 times 10, that's 100. Square root of 100 is 10. Well, it has to have greater speed of 10 meters per second, more than before, right? So that's one of the problems. Totally want you to know, and totally know that. That formula is only related to this loop-the-loop type of problem, circular motion, vertical plane. Actually, I take that back. It's not just related to this one problem. It could have been, again, the bucket. Professor is doing a demonstration in class and spinning a bucket of water round and round. If that's the case, the radius is actually usually goes from the center of the object all the way out. So you're just considering the whole entire thing R. You don't ever have to be like, oh, L, and then you got to add a, just know that that's usually. So let's just say they give this 2 meters. Same question. This guy is in this class again, whipping this thing around. Boom, boom. What is the minimum speed he has to have so that when it reaches the top, the water doesn't spill out? It's the same question. The physics is the same question, I should say. What minimum speed does the car have to have so the passengers don't fall out of the car if they're, no seatbelt on, for example? Same thing. Vmin equals the square root of R times G. 2 times, I have to do it again, but it's the same answer. Whatever I got before, 4.47 meters per second. The same answer that we had before. The physics is the same, it's the same formula. Again, it's relating just to the top of a circular motion path when you're talking about vertical motion. Totally star this, totally put this in your to know list. Equations to know. The other side of that, the inverse of that, is now the problem where a car goes over a hill. This is, I say the other side of it. It's like, now something's on the top of this, like the inverse of this. Car is driving over a hill. This is the other question they provide. I'll show you what the question usually is, how it's stated. A car moves at a speed v as it passes the top of the hill. Passes, I guess say the word through. As it passes through the top of the hill. At this point, speed is v. The top. I didn't draw it perfectly, but it's at the top of the hill. Derive a formula for the normal force. Okay, let's try our free body diagram. Well, let's just say the car is parked over here. Parked car, free body diagram. Now it starts driving along, and then it goes over this. What would the free body diagram look like now as it flies through the top of this here? Should we draw this the same? Should we draw one of these bigger or shorter? Just remember that if you are in this car, and this is like the seat, and always, this is how I thought of it. I thought of a scale, and I always imagined myself sitting on a scale. So I'm imagining I'm in the car. That is your imagination sometimes, is it? Imagine you're in the car, sitting on a bathroom scale. Fn is what the scale reads. You need to know that. The normal force is what the scale reads. If you're sitting on it in the parked car, it's just going to read what you weigh, of course, right? If you're sitting on it, put it on your seat and you sit on it, just read your weight. However, when you go over the hill, is the bathroom scale in that moment going to read more than what you weigh, less than what you weigh? or the same as what you weigh. Now just put yourself in your mind in that position. You're driving over the hill. You go fast enough over this hill. What does your body do at the top? Fast enough, I'm sure all of you at least done it once, fast enough over a little hump like this, your body lifts up a little bit. Your body starts to kind of come up and separate a little bit, comes off of the scale. It doesn't go flying and your head doesn't hit the ceiling. We know that. But there's just a little bit of upward motion that your body has as it slowly lifts off of the scale. And then as you come down, of course, your body boom, sinks back into the scale. And then, of course, as you go over here, straight on the flat part, it returns to this. These will be the same. The question is, again, how would you draw that for the middle part? Well, since you're coming off of the scale, and the scale is what the scale reads, Fn is what the scale reads, and you're coming off of it, there's less pressure on the scale. The normal force is going to decrease. It's going to be less than what you weigh if you're coming over the top of a hill. And that's what they're asking you to solve for. How do you derive a formula for Fn? Now remember, circular motion still works even when it's not a full circle. As long as you can inscribe a circle into a certain portion of that motion, which I've done here, then circular motion, I can still use the physics of circular motion as it moves along this part, which includes the top part. Again, I didn't draw it perfectly. It's supposed to be right at the top. And therefore, R is this. And they would probably say here, derive a formula for Fn in terms of R and any other fundamental constants. What are the other fundamental constants they're talking about? They're talking about G. How do we do that? Well, let's try. Here's our hill again, like this. Here's our circle. We know as the car goes over the top, the downward force, mg. The normal force is up, and it's Fn. The convention is that any forces towards the center of the circle are plus, and any forces away from the center are minus. That tells us that Fn will have to be minus, and mg will have to be plus. All right, let's use the same rule. The net force equals mv squared over r. We've got two to consider. mg is really the first one. I'll just leave it as fg. Minus, because it's away, minus Fn. We express Fg as mg. Solve for Fn. Well, I guess my mind, I think of just moving this over as a positive, because you always want to solve for a positive variable, and move the other one to the other side, right? So what would I get? I get mg, Fn comes over as a plus, this comes over as a minus. Didn't need to write it backwards, but that's what it would be. Usually you write Fn equals, not Fn on the right side, but same idea. mg minus mv squared over r. Notice that this is the same formula as what I had done with you guys in class, which was the scenario of zipping a bucket around and solving for the tension. Just pointing out there's a connection there. The tension for the bucket at the top was like this, the bucket problem. And then the tension is up. Tension is here, is up. And so the tension at the bottom was mg plus mv squared over r, because you always feel more upward force than what you weigh at the bottom. While at the top, it was, I have to think about that. Was it mg? Actually, mv squared over r minus mg. So it's similar. Notice that it's similar, but not exactly the same. This result for that is very similar to this. Not exactly the same in terms of the signs, but that's how you do it. That's how you solve for the normal force. if the car decides to just park up here, then the speed of it is 0, v is 0, the normal force returns to mg, which is what we already knew before, right? For the parked car, we already said that the normal force has to be equal to mg. And that's what this would give you. You put 0 in because it decides to park there, right? So those are two common examples, really three, to be honest. There's the bucket problem, spinning around so the water doesn't spill out. There's the hill problem that I've just gone over with you. And then there's the loop-the-loop. They all have a lot of similar physics. And in 99% of the cases, the problem is going to be relating to the bottom of the path. Well, not on the loop-the-loop. The loop-the-loop problem is almost always referencing the top of the path. However, if they're giving you the bucket problem, then they're going to be talking about these 2 points. Or the hill problem, of course, you can't talk about down here because that's inside the earth, but they would be talking about the spot right here. Let me lastly say, if they, in this problem, said, what speed causes Fn to be equal to 0? What min speed? And why would they say what minimum speed? Because if you're going fast enough at some particular speed, your butt literally comes off of the seat. If you're going fast enough over the top of the hill, your butt literally will lift off of the seat. It will leave the scale completely, and the scale will read 0 for that brief moment, till, of course, you come over the hill, and then boom, you get pushed back into the scale. But if they ask that question again, what minimum speed causes no normal force? Essentially what they're saying is what minimum speed, and that they're really usually referring to the normal force on the car. And in that case, it means that the car is literally, the tires are coming off of the road for a brief moment, and then they'll make contact with the road again right here. It's not going to go flying like a jump. They're just going to barely lose contact with the road for a brief moment and then make contact again. And if in that scenario, the wheels lose contact with the road, your butt will come off of the scale just for a brief moment. So if they ask that, how would you solve that? What minimum, any faster than that, it's still true. You'll still come flying off the scale. But what is the minimum speed we'd need to see that happen? Fn to be equal to 0. You use the same formula. You just plug in 0 for Fn. 0 equals mg minus mv squared over r. And then I would solve for v. Now I'd have to put min in here, right? So I'd end up with, again, a little bigger. 0 equals mg minus mv squared over r. By just plugging 0 in for the normal force, since I'm going at that fast enough where my butt separates from the scale and it doesn't read anything. And then I'd solve for v min. I'd get them on opposite sides of the formula, right? I'd end up with mv squared over r equals mg by just moving this as a negative term over to the other side. Notice again, m's cancel out, not surprisingly. Doesn't depend on how heavy your car is or how heavy you are. If your butt separates from the seat at that speed, your little brother, who's far less heavy than you are, his butt will separate from the seat too. Oh, and little Mousy that was happening sitting next, little Mousy came off the seat too. That's what it's indicating. Doesn't matter whatever the mass of all the objects in the car, if they are free to move, would slightly lift off of the surface that they were on for a brief moment, and then get pushed back into that surface. Oops. What did I do? I lost my page, which was, sorry, right here. So now I would just solve for v min. Square root of r times g. The same result that we had before. This is the same formula that gives you the minimum speed at the top of the path so that the water doesn't come out. The minimum speed for the bucket problem is the square root of r times g. What's the minimum speed for this case for someone, the wheels to just come off of the road and produce no normal force? Same formula. V min equals square root of r times g. Interestingly, I show you one last connection, if I could. If I were to do this, just back to orbits for one moment. You remember this? Now, I'd also like to point out, recall that Gmm over r squared, which is the force of gravity, is also equal to mg, right? Those are two formulas that give us mg. So the formula for g out at some distance, g equals gm over r squared. So if I had actually multiplied this back to the other thing I was just doing, times 1 over r, and this times 1 over r, what would I get? I get v squared over r Am I saying this right? I'm not sure. Give me a second. Yeah, I am saying this right. I'd have v squared over r equals the same thing over here, gm times 1 over r squared, which is just over r squared. Gm over r squared is actually g. This is actually g, out at some distance. I'm referring to orbital motion right now. Planet Earth and Moon, and we set these formulas equal. You remember? Interesting. What do we get? This is the expression you get for g. That means you get v squared over r equals g, the velocity in orbit, is equal to r over g, whatever it is in orbit. It's not 9.8, it's whatever g is in that orbit. But interesting, when you solve for v, what do you get? Cross multiply rg, and then square root, right? Square root. Wow, that's crazy. You get the same formula for the speed of a planet in orbit around the sun, for example. As long as you know what g is for the sun out at that distance, it's not going to be the surface gravity of the sun. Or for the moon and the earth, it's g of the earth out at the moon, not 9.8. That's only on the surface of the earth. It's g, whatever g is, all the way out at the distance of the moon. But whatever that distance is out by the moon, times whatever Earth's gravity is out at the moon, that gives you the velocity of that object in orbit. Interesting, right? To me, at least. If I were to Google, let's just see, the radius, how far away is the moon? Distance to moon in meters. 384 million. Average speed of the moon. We already knew it before from the other day when you guys had to calculate it, but I just wanted to show you again. In meters per second, of course, but you can see it. Kilometers per, so it's in meters per second, you just shift the decimal over 3 to the right. So it's 1,022. So the speed of the moon is 1,022 meters per second. And what was the distance to the moon? 384 million. Let's just see. That means I could technically calculate the speed of the moon by doing 384 million, which is times 10 to the 6th for the distance to the moon. That's right. I still would need to calculate g out at the moon. Forgot about that. I wanted to try to just at least prove to you. It would take a little extra time. I'd have to work out what g is. Gm. This would have to be g of Earth out at the moon would have to be g times mass of the Earth divided by the moon's distance squared. Too much time. But just take my word for it. It's an interesting connection. If you worked out what Earth's gravity is, not 9.8 again, but some far less number, out at the distance of the moon, and plugged that number here, and multiplied it by how far away the moon is, and did this, you get that number. And it shows you that there's such a connection. It shows that it's correct. And then that's actually the formula that we're just getting for the spinning bucket. And the same formula for the car that comes over the top of this. What's the minimum speed necessary so that it just separates everything separates from whatever's underneath it. The car does, and so does the people, and all the normal forces go to zero just for a brief moment. V min equals the square root of r times g. Same thing for the loop-de-loop. Minimum speed so that this doesn't separate. V min square root of r times g. Trying to see if I had another example of this on here. No, I guess not. No, this is what we were just doing, right? Yeah, coming over the top. The minimum speed is, again, these cancel and you're left with v squared equals the square root of r times g. Again, for the car, scenario 2. So worth knowing. There's so many different types of problems that do show up, like I've just shown you, and a lot of them tie into the same physics, and in that case, the same formula. All right. I don't have anything else to say. I think I finally covered what I wanted to cover. All right, guys. Thanks for watching. See you guys soon.